Hello, so today we're going to go over a problem. We have a Stefan tube and you have acetone and methanol at the bottom and air flowing over it. We're kind of given these kinds of things, Stefan Maxwell coefficients, um, mass fractions, temperature and pressure. Um, yeah, so what we're looking for is a kind of an estimate of order of magnitude for for n for molar flux. Um, yep. So let's go ahead and get started. So first, we can kind of start. This is a formula from 126, I believe. So you can go ahead and start with the driving force of 1, which would be I put it as acetone, dPc. So you have two interactions with acetone. You have acetone and methanol, and acetone and air. So you can start with Y1 all over C. Getting better at these. 1, 2. Okay, so this is the interaction between acetone and methanol. Y1 N2 minus Y2 N1 all over concentration times the Stefan Maxwell of 1, 2, which is acetone and methanol. And we can do the same thing for interaction between acetone and air. So in the same method, you just basically replace 1 with or 2 with 3. And 3 minus 1. Okay. See. God, they're ugly. 1, 3. Okay. So, looking at this formula now, we know that the molar flux of air is going to be equal to 0. This whole thing is going to 0. And that's because none of this air is diffusing down into the tube. It's just flowing over. So now I can rewrite this whole thing dz y1 n2 2 minus 1 2, and then we're just left with this. So y3 n1 over c 3. Okay. Yeah, so that's a pretty pretty important step. So next thing that we're going to do is okay. So the next thing that we're going to do is we're going to introduce the variable eta. I'm so bad at drawing this. And that's going to be equal to z over delta. Okay. That's an awful z. Z over delta. Okay, so what we can do with this is we can kind of we can play with this a bit, and what we can put it right here. So we have the driving force in respect to z. We can do the same thing here and use the product rule. So we know that it's dz, so put dz here, and then d eta, and this would also be d eta, right? So we know what this is going to be, right? Just from this, we know that this is going to be equal to 1 over. Let's rearrange this. Make sure that's right. Z n over z. Yep, 1 over eta. Okay, so then this is going to be equal to the driving force in respect to eta times 1 over delta. So yep, so now we can kind of put this back into this. I'm just going to multiply the delta and put it on this side. So this is going to be dy1 over d eta is equal to delta. We're just going to multiply it on the other side. So delta, and then this whole thing, right? 2 minus y2 and 1 all over c 2 minus y3 and 1 over c over 1, 3. Okay. So now we can kind of like start playing. We're looking for the order of magnitude. So we can start playing with, these kinds of things. We know we can kind of create a variable, and that would be equal to c. You see it on the camera. C. Oh, Jesus. Let's see if I can draw Stefan Maxwell quick. So there we go. Be 1, 2 all over delta. Right? And we can solve for C also. Make sure that you can see it on the camera. C would be equal to P over RT. P over RT times the Stefan Maxwell of 1, 2 all over delta. Okay, so that's basically 1 over what this is right here. So this would be on the bottom right here. So we know we're gonna do a estimate of order of magnitude. So basically what that means is that like we know that pressure is 10 to the 5th. We know what else? We know that the Stefan Maxwell is 10 to the negative 5th. And then that would be over D. We know that D is 1. And then we know that we know that T is going to be 10 to the 3rd, right? And then we also know that R is equal to 10 to the 3rd. And that should give us 10 to, is that right? Oh, sorry, I already repeated myself. Okay, yeah, that's why I was confused. Okay, so that's already there, 10 to the 3rd. Yeah, I need to write it twice. So that should be equal to 10 to the negative 3rd. Sorry, looking over there. 10 to the negative 3rd. Okay, so we can put that in here, and this bottom part, all of this. And we can kind of ignore this right now. We don't really need it. And you'll see in a second. And also this has to be 1, right? This is from 0 to 1. This is 0 to 1. This is 0 to 1, I believe. Yep. So then we can just put dy1 over dn over kind of approximating these. This would be 10 to the negative 3, right? And then we know that y1 and y2 they have the magnitude of 1, right? So to be able to, since this is 1, we know that these two things are approximately equal to each other. Well, they're equal to each other, right? But yeah, they're equal to each other. So now we can, sorry, they're not equal to each other. Sorry, one minus this is equal to this. So we can kind of do an order of magnitude estimates. This is 1, this is 1. So then this is 10 to the negative 3. So we know that this times this would have to be equal to 10 to the 3rd. Because 10, 10 to the negative 3. Sorry, losing my mind. 10 to the negative 3. So that would be equal to 1. So say it's 10 to the negative 3 minus 10 to the negative 3 all over 10 to the negative 3. That would be equal to 1. So then we can kind of say that, because of that, we can say that N1 and N2 are both they have a magnitude of 10 to the negative third. Okay, so now that we found this, we can move on. That's the scaling. We can move on to the coding part of this.
Okay, so now we're going to move on to the coding part of the problem. We already did the scaling and the estimate of size for n1 and n2. So we're already given these values from the problems I talked about before. And these are the calculations for F1, our F values and our concentration. So we can start by importing numpy as np, and then from scipy dot integrate, we're going to import solve underscore IBP. Jeez, awful typing. IBP. And then from scipy optimize, we're going to import root, and then from plotly dot subplots, we're going to import make underscore subplots, and then we're going to import plotly dot graph underscore objects as go. Sorry, I had to space one. Okay. So we're going to use a solve initial value problem for the driving force, and then we're going to use root to reevaluate n1 and n2, and then we're going to use these two for making our plots and subplots. So we can go ahead and get started by making a function fn. It'll be we first have to say what's in the arrays. So n, the first value of the array will be n0. It'll be acetone, and n2 will be the second value in the array. And then we could put another function called dy, and it'll be terms of eta and y. And then we basically have to say what y1 is. So y1 will be the first value in the array y. Same thing with y2. And then y3 will be in terms of y1 and y2. Okay, so now we have to decide what we want to return. And what we're going to return is the array for driving force. So I believe it's that. So the first value in the array will be the interaction between acetone and methanol and acetone and air, and then the second part of the second value will be methanol interacting with acetone and methanol interacting with air. So it should be y1 times n2 minus y2 times n2, or y2 times n1, and that's all over f12. And then the other value, since we determined that n3 was equal to 0, is y3 times n1 all over f13. And then the second part is the interactions between methanol and acetone and methanol and air. So it should be y2 times n1 minus y1 times n2. And that's all over f12 subtracted by, or I guess we're subtracting y3 times n2 over f13. Yeah, that should work. Okay, so now we're going to choose the resolution. That's going to be solve IBP, what we brought in before, and it's going to be the driving force from 0 to 1, 0 to 1, and then we're going to put y1 initial and y2 initials as our variables. And then our method is going to be radu. And then our dense output is going to be equal to true. Okay, and then we're going to return. Actually, these go back one. And then we're going to return the resolution in terms of. Okay, so the next part of this is the roots. So we're going to have res r, which is just the resolution in roots, with root f, and then n1 initial, and n2 initial. And then we're going to, we have to actually say what n1 is now, so it'll be res r x0, so we get the first value in the array x, and then n2 res r x, and it'll be the second value in the array. So then now we can basically copy and paste what we put above, and what that is us reevaluating what n1 and n2 are, but with those new values. And we can actually copy and paste this one too. Yep, and that should reevaluate it. And then we can move on to the actual plot. And that'll be equal to np line space 0, 1, and the number is equal to 51. So, and then we have to attach the solution to the plot. So the solution is equal to res.solution eta plot. Okay. And this last part is making the lines and the figures. So like making the titles and then making the actual, drawing it. So the figure is equal to make subplots. Rows equal to 1, columns equal to 1, and then x title is going to be equal to eta, and then y title will be equal to mole fraction, and that'll give the labels for the axis. So then the other thing that we need to do is actually put in our lines into the graph. So it'll be x is equal to eta plots, and then y is equal to the first value in the solution. And then the name is going to be equal to acetone. Okay, now similarly we can do the same thing for methanol and air. The only big difference is that we need to put methanol as obviously the second value in the array, and then air needs to be put in terms of methanol and acetone, so we need to subtract it from the solution of it's the solution of acetone and methanol. So it'll be 1 minus. Okay. Let's see if we can run it through. Oh, sorry. It should be scatter. I'll go. Let's try that. actually go dot scatter, but why? Oh. Alright, let's try one more time. Okay, so as you can see, so as air increases, or as eta increases, the air increases, the mole fraction of air increases, and the mole fraction of methanol and acetone decrease. So that's what we're looking for. Thanks.